Welcome back. So today we're going to talk about the mathematics of prediction, also known as low rank optimization approximation. So I'm Professor Wu. Let's get started. So we previously talked about this really important thing called the spectrum theorem. The spectrum theorem basically says that a matrix like this, could be broken down into its core essences, which we call them eigenvalues and eigenvectors, right? So the numbers in front of these are eigenvalues, and then these vectors are the eigenvectors. And eigenvectors kind of represents the core essence of the matrix, right? Depending on what the matrix is describing. Now, the conclusion from this is that notice that the summation of them ultimately creates the matrix A. Therefore, if the eigenvalues are 0, 0, 0, then it does not contribute. So these eigenvectors must not contribute to the matrix ultimately. In fact, these small ones also don't really contribute very much. Right? This help us leads us into categorizing eigenvalues. Yeah, we're going to break them down into four categories. The first one is trivial eigenvectors. It means they don't contribute. Those are the cases when the eigenvalues are 0. And then there's the almost trivial, which they don't really contribute because the eigenvalues are pretty small compared to the rest of them. And then we have the core eigenvalues, core eigenvectors. They contribute roughly 95, even up to 99% of the essence of the matrix. And last one is dominant. The dominant eigenvectors, these are it's just one. It's essentially the eigenvector with the largest eigenvalue, right? So largest absolute. So it could be negative or positive, the largest absolute. So in this particular example, this will be the dominant because it has the largest eigenvalue. These will be the core. These are the core. And this will be almost trivial, and these will be trivial. All right, so the spectrum theorem tells us that we don't need trivial eigenvectors, right? So it's very clear. If there's a 0 here, we don't really need it. However, there is a second way to write the spectrum theorem. Notice how this could be written this way. So, well, you can just multiply it out. Well, after you multiply this whole thing out, you'll see that they're equivalent. So if we don't need this, right, this is equivalent to getting rid of some columns and rows. So you don't need this vector anymore, so get rid of this column. You don't need the column and the row here for the eigenvalues, and you definitely don't need the row here because that's V3, right? So as a result, you can compress it, and this smaller multiplication will still yield the exactly same matrix. All right, so first exercise, pause the video, and let's say that you are modeling this like 4 by 4 matrix, and this is the eigenvalues. Now, notice how we have two dominant, core eigenvalues, a almost trivial and a trivial. So what I want you to do now is to write the Python code that verifies that if you were to take the eigenvectors, eigenvalue, eigenvector, multiply them together, the spectrum theorem says that it will reconstruct the matrix A. Okay. After you verify this, then try to see if you could get rid of the trivial one. So get rid of this one so you have a smaller matrix, and then see if you're able to essentially get the matrix A back again. And very lastly, what if you just get rid of this one as well? So you only have this matrix. You should still be able to get roughly the matrix back. Okay. You can use the starter code to avoid typing a lot, but yeah, this will speed things up for you. All right, so here's the solution. You can pause the video and check it out. You also have the slides. All right, so this is the same idea for SVD. So remember, we had like one path which went into, if it's like symmetric, right? Symmetric. So that's the eigen decomposition. And then we have the other one as SVD, which is non-symmetric. So For non-symmetric, what we end up having is that A becomes V sigma U transpose. Well, in this particular case, the idea is the same. If you have certain eigenvalues or singular values, in this case, is equal to 0, you can get rid of those rows as well as columns, right? So this is the same idea translates. And now what I want you to do is pause the video again and see if you can do that. So here's the non-symmetric matrix. Calculate the U, sigma, and V associated with this matrix and apply the same idea and remove the trivial. After you remove the trivial, you should still be able to reconstruct the original matrix A. All right, here's the solution. Part 2, part 3, part 4, part 5, and then that's part 6, part 7. This is a very long exercise, part 8. So you can also do singular value decomposition here with the command svd if you are using numpy. All right, so the point of this class is let's talk about this case of missing entries. And in the class, the idea is that we will run a quick experiment. The experiment basically says that you have a matrix. You can download this file. You can try yourself this file, and it's 1,000 by 1,000. All right, so it's a huge matrix. However, one element is missing. You don't have this number. The question is, are you able to look at the rest of the matrix and use the rest of the matrix to predict this number? And the answer is yes. We can essentially use SVD to do this. How is this possible? Well, remember that SVD, you have any matrix, right, can be broken down into the singular value components. So this is the eigen vectors. So these are the eigenvector for the row space, eigenvector for the column space, and this could be written out this way, just like the spectrum theorem you guys are used to. So what happened is, if you have a giant matrix with a missing element, you can just give it any number. Let's say you use the average or 0, right? You pick 0 or average. Now there's a number here. I'm not saying that's the right number. What you can do is essentially do SVD and then spread out all the spectrums or using the spectrum theorem. So you now know all the core components. And what you do is remove the trivial and almost trivial. So just remove those and look at only the core components. When you do that, this allows you to reconstruct the best approximation of A. And once you have this reconstruction of A, which we're going to call A tilde, this A will essentially give you the value here. Right? It approximates the value. And that's the general idea of this experiment. If you have to, when you're at home, make sure you give this experiment a try. You should be able to get the same result. Okay. So here's the exercise. Pause the video. I did give you the solution as well as the code, starter code, and it does work. All right. So this idea then leads us into prediction. Let's say that you have you're collecting data. And when you're collecting data, you sometimes are missing specific events that it hasn't happened yet, and therefore you can't really fill this in. Right? So in those cases, we can use the exact same thing we just did to reconstruct A, right? So if we use A and then convert it into SVD, and then essentially chop off the trivial and the almost trivial, reconstruct A, it will essentially give you the best approximation value. Right? If you think about how we make predictions, right, we collect historical data, just like what we did, and then we identify the key components, V1, V2, V3, and for each component, we remove the less important one, and then we reconstruct the best prediction. So this is the ability to predict things, and it's very, very powerful. Now, this matrix was this algorithm. You can see that it is how Netflix, for example, originally used to identify recommendations. So you have seen some movies, some shows, and you haven't seen other ones, right? So the ones you have not seen are the missing elements. So if those are missing, well, this means that you can essentially use singular value decomposition and approximate the values here and here, right? You can approximate the value. Once you have the number 8, 1, 0, 0, 1, 2, you can say that, well, this one seems to be very, very high. Why don't we recommend this? Okay. So in the case where you have a lot of missing values, we call these matrices sparse, right? They're only numbers sparsely. However, there's very few, so it's dense. So the difference is sparse and dense is just how many missing values there are. All right. So like I told you, Netflix originally basically used this algorithm. You can use this for dating sites, like who would be likely compatible with you, or you can use this for image processing. Like notice how there's a little error here, and by using SVD, also local low rank in painting, like you can clean these pixels up automatically. All right, so how do we quantify ignorance? There are many ways to define intelligence. So, for our case in this class, we're going to say that intelligence is the ability to correctly predict the outcome of hypothetical situations. For situations you have not seen, like identical situation you have not seen in the past, how do you predict what you do that give you the outcome you want? And we're going to define that as intelligence. And therefore, the opposite of intelligence is ignorance. So intelligence is a lack of ignorance, and we can measure ignorance by error, right? So let's say you have this matrix, and you have missing entries, certain entries, and because of these missing entries, when these events happen, you need to kind of make predictions. If this happens, do I know what to do? For example. So your ability to predict the missing entry is essentially a way of measuring intelligence. And then we can quantify that. We can quantify by identifying the error. So the larger the error, the more ignorant you are, because when I say error, so a hat right here is what you predict, and this is the truth. So the difference between what you predict and the truth is the error, right? So the larger the error means you are less intelligent, right? And you're more ignorant. So this error is a measurement of ignorance. And you can also normalize it. So you divide it by the original A value, AF. Now, by the way, this F, if you remember, this is the Frobenius norm. Okay, this is the Frobenius norm. So you find the difference between the two matrices, and then you calculate the Frobenius norm. So since it's a norm, I probably should have done this. Okay, so did this not load? Well, I have a couple of them that did not load. Here we go. It is loading. All right. So for the final exercise, what I want you to do is to simulate intelligence. Basically, you're going to take this data, right? So this data is a big matrix, and you're going to purposely set a bunch of them to zeros. So you're going to set a bunch of these to zeros. So initially, you're going to set 10%. And these zeros will just represent your ignorance, right? And then you're going to try to predict. You're going to try to predict these values. If you're able to predict this value, then you can measure the error. Right? So you can see that if you're missing only 10%, the error is pretty low, right, when you make a prediction. If you're missing 20%, then the error gets higher. 30% gets higher. So all the way, if you're missing 90% of the data, which you just set it to 0, you're going to get a pretty big error. You're going to get so this right here, it's essentially simulating like intelligence from past experience, from experiences you've had. Are you able to predict the outcome of a hypothetical situation? Okay, so all right, so this is it for this lecture. I will see you in the next lecture.